Hello everyone, I hope you are doing fine. In these and upcoming sessions, we will talk about two more properties of Hilbert spaces. But before you watch this video, I would recommend you to watch my previous video where I have given some basic properties of Hilbert spaces. Now I have divided this topic in three parts. First is the Cauchy sequence, second is the separability of the Hilbert space, and third is the completeness of Hilbert space. Now to understand the separability and completeness of Hilbert spaces, we must know about Cauchy sequences. So what is a Cauchy sequence? A sequence AN is called a Cauchy sequence if for every epsilon greater than 0 we have capital N which belongs to the natural number, such that for small n and small m greater than or equal to n we have modulus of am minus an less than or equal to epsilon. Now what does this modulus of am minus an mean? It means that the distance between two terms am and an, and this distance is less than or equal to epsilon. That means these two terms are within epsilon distance of each other. Now suppose I have a sequence like this, an. Here the terms of this sequence are represented by black lines. Now what does this definition says is, for every epsilon greater than 0 you can always find a number capital N which belongs to the natural number, such that all the terms which succeed this number capital N will be within an epsilon distance of each other. Let's look at this way. Suppose you can give me a number epsilon greater than 0. Then if I can find a number capital N such that, so I will show you here, I have found a capital N such that all the terms which are ahead of this capital N are within epsilon distance of each other, then the sequence is a Cauchy sequence. In nutshell, a Cauchy sequence is a sequence whose terms come close to each other after some point. Now, the limit of the Cauchy sequence may or may not exist. You will understand this thing later. Now, let's look at the separability of the Hilbert spaces. What is separability? Suppose we have a universal set capital U and I have its subset capital X. Then if the subset X is countable and dense, we say that U is separable. Capital U is separable. Note here that you should have the subset of a particular set to be countable and dense to call that particular set separable. For example, here if I show X as a countable and dense subset of U, that means U is separable. Now let's look at the countability property. Suppose I have a set of real numbers like this, and then we have a set of rational numbers whose elements are given by P by Q, where P and Q are integers. Now this set Q of rational numbers is the subset of real numbers. Now since the integers are countable even though infinite, this subset Q of real numbers is countable. Now let's look at the denseness property. Suppose I have a number alpha which belongs to the set of real numbers. Then in order for R to be the dense set, you must have the alpha in the set of rational numbers Q, or there must be an element in Q which is arbitrarily close to the number alpha. So let's look at this in detail. Suppose I choose alpha as root 2, which is a part of real number space, but not a part of the irrational numbers, because it cannot be written as a fraction of two integers, or we can say that it doesn't have terminating decimals. But I can always find a sequence in rational numbers like this: 1.4, 1.41, 1.414 and so on. Note that All these numbers are rational because they can be written as a fraction of two integers. For example, 1.41 can be written as 141 divided by 100, where 141 and 100 both are integers. Now, if I go forward term by term by increasing the precision, I will eventually approach to the actual value of this sequence or actual value of root 2, which is this sequence is approaching. But note that this sequence approaches to root 2, and this root 2 doesn't belong to the set of rational numbers. But I can always find a rational number in this sequence which is as close to root 2 as I want. This denseness is determined by the closeness or the existence of the term which is close to root 2 as much as you want. So this was the discussion on separability that we had. So in the next video I will talk about separability of the Hilbert space. Thanks for watching the video.